record.
Okay. Okay, so to put this into this form, so you can apply the quadratic formula, which you know how to do, okay? We have to have a zero over here, and we have to do this by valid mathematical operations. So the way we do it is, first, let's just write it out again. X squared equals 4x plus 6. And let me actually, it's probably blocking the board. Move this over as far as I can, so the camera has a little better angle. Okay, okay, so we have this. Now, what we do is, okay, we got to get 0 over here. We can't have 4x over here. How do we get rid of 4x on this side? Well, we subtract 4x from both sides. And 4x minus 4x is 0. So we get okay. Now we do the 4x and the minus 4x. We kind of change the order of these terms. So the 4x is next to the negative 4x. So we can clearly see that we get 0. We're going to get 0 there. Okay. And now we still got 6. We don't have 0 on this side, although we've got a 0 where the 4x was. I don't need to leave this 0 here because 0 plus 6 is just 6. I just kind of want to emphasize that we're getting zeros over here. So now we get x squared minus 4x minus 6 equals 0 plus 0, or just x squared minus 4x minus 6 equals 0. Okay, and now we use the quadratic formula. Okay, let's do another one. Let's say you've got 4x squared plus 9 equals 3. And you put that into the form, we've got a 0 on this side. Using valid operations. The valid operations you have to use are just you can add or subtract the same quantity on both sides. Okay, got to use that. We add or subtract the same thing on both sides. Or we can multiply or divide both sides by the same thing. Those are our rules. Okay, can we use those rules to do this? In this case, we add or subtract the same quantity. On both sides. Okay, now I didn't have an X on the 9 here. It actually makes a better problem if I put an X there. So let's do it with a 9X here. Okay. So if you're watching, you can go ahead and do this. But what we want to do is we want a 0 on this side, right? To get a 0 on this side, what operation would we do? What would we add, subtract, multiply, or divide by 3 to get 0? Show me your fingers. Well, actually, let's just talk about it. Okay, now we want a 0 on this side. Again, the question is there something we can, an arithmetic operation we can do to get rid of that 3 and make it a 0? Okay. Well, you pretty quickly saw once you focused on this side, what some people wanted to do was focus on the 9x or something else, okay? But no, we want to focus on this side to see what it takes to get 0. And then as soon as we focused on that, saw exactly what we did. And here's our equation. To get a 0 on this side, we're going to have to subtract 3, okay? Now, of course, if we subtract 3 on this side and not this side, the equation is no longer equivalent. It's not balanced anymore. We've got to subtract 3 from this side as well. Now, when we do that, we get four x squared plus 9x minus 3 is equal to 0. And then we can use the quadratic formula. Okay, let's do another one. What could we do to this to get a 0 on the right-hand side? Okay, now a little bit of minor confusion here. And we've got this. What are we going to do to both sides? Well, you know, question, well, we have to do something with that x. It's simpler than that. We've got 4x. So if we subtract 4x, we got something minus itself. And when something is subtracted from itself, you're going to get 0. Okay. So if we do a minus 4x over here, and I meant to write that in purple, so I'm going to do that. At least so. Halfway purple. Okay. And we got to do the same thing over here. Okay, now what do we have on this side? 4x minus 4x is 0. And we have negative 3x squared plus 7 minus 4x equals 0. Now, this isn't quite yet in this exact form. Okay, can you see why this expression isn't in the form of this one? Okay, now the common error, you know, I just asked, okay, what's the value of a for this expression? Okay. And the answer I got from some people was ax squared. Well, a is not equal to, I'm sorry, the answer I got from several people was a is negative 3x squared. Something I see a whole lot when we start using the quadratic formula, and that's not quite right. Because if a was negative 3x squared, if you substitute negative 3x squared for a, you get negative 3x squared, x squared. Okay? If you replace a with negative 3x squared, you get a couple of x squared, so you only got one x squared. So the point is that a is negative 3. If you replace a with negative 3, you get negative 3x squared, which is what you have here. Okay? So, first place, a is equal to 3. Now, what's b equal to? Okay. So we identify a, b, and c. A is whatever's in front of x squared, and that's negative 3. Because of the order of these things, some people are going to say, well, b is the next thing, so that'd be 7. Well, no, b is what's in front of x. So b is what's in front of x, which is not 4, it's negative 4. Make sure we see that negative sign. So b would be your negative 4. And what would c be? Well, everybody knew right away, well, that leaves 7. So you 7. Well, 7 is the thing that doesn't have any x's on it. Okay. Now, my point is, it can be a little confusing. You know, a lot of people are going to want to say, well, a is this one, b is this one, and c is this one, without noticing that b is whatever's in front of x. and b has to be -4. It's less confusing if we then write this thing in this form. Because now everything's exactly where we want to see it. Okay, so I would say that once you get this form, it's not quite this. Because the x squared comes first, then the x, and then the number. Okay, so we do it this way: x squared first, and then the x, and then the number. So we just, instead of writing the 4x here, we write -4x here, we write it in front of the +7. We get this. And now we can use a quadratic formula. Okay, let's do some more of this. Let's make sure we get the gist of this. Okay. This is important because these are operations that we can always do to both sides of an equation. And not everybody is getting those operations right, partly because the format that people are using. I'm not going to address that right now. But, okay, so let's say we've got this. 9x minus 7 equals 8x squared. And we want to get 0 on the right-hand side. So what are we going to do? Okay, so what do we do here? Well, we have 9x minus 7 equals 8x squared. What do we do both sides? Well, it's hard to do much to both sides because I can't find my purple chalk all of a sudden. How did that happen? I got a little nub of this stuff. How does it keep happening? My chalk keeps wandering away when I turn my back. Well, it's obviously that I misplaced it. Okay, so anyhow, we're going to subtract 8x squared from both sides. That's a little sloppy right there, but I think you can see what we did. Didn't leave myself quite enough room to write it out. So what we get then on the left-hand side is 9x minus 7 minus 8x squared. And when you subtract something from itself, it gives you 0. Basic principle. Okay, now is this in this form, or do you have to change the order of those things? Well, I'll tell you, it's not in that form. You do need to change the order, okay? Can you put them in the order so you have ax squared plus bx plus c? Okay, so we put it in order. The negative 8x squared should go first because the x squared term is first in this form. And then the 9x plus 9x and minus 7 is here. 9x is positive, so we're going to make a plus 9x. Okay, so now it's in the form, and you can identify A, B, and C, plug it into the quadratic formula and get your solution. Maybe you can factor it too, but in general, in the real world, almost every time you have an actual quadratic equation, you need the quadratic formula. It's very rare that you find one little factor. Okay. Let's try another one. I'm going to try as hard as I can to confuse you because I think and if I can't manage to confuse you, then that's really good. Okay, so that's your goal. Try not to get confused, do it carefully and step by step. Okay, well, everybody got this one. Okay, this one. Make sure we got 5 plus 3x squared equals 12x. Emphasize what we do. We need 0 over here, so we subtract 12x. And we do the same thing here. And we get 5 plus 3x squared minus 12x equals 0. Now, it's a little inconvenient to have things in this order. You want things where the x squared is first, the x is second, and the c is third. Generally, when you write down an expression with powers of x, you want the biggest powers first and descending powers. Okay, because it's just easier to look at. If you look at this and try to apply that, you got to be really careful. You know, you would look and say, okay, let's see, what's in front of x squared? Yeah, it's 3. You do that. What's in front of b? Well, it's -12. I'm sorry, what's in front of x? It's -12. And what's c? Well, it's got to be 5. You can see it here, but you got to look a lot more carefully than you do if you put it in the form 3x squared minus 12x plus 5 equals 0. Okay? If you put it in this form, then you know exactly where to look for the coefficients a, b, and c. Okay? In this form, you got to be careful. So you try to avoid making yourself, you try to avoid writing it in a form that's a little bit more prone to an error. Okay. So this is good. Now let's try this. And I've got a little glitch from the board right here, but I'll try it. I'll go over it anyway. Okay. So let's say we've got we know we've got 2 terms on this side instead of just 1. So see what you think we should do with this equation. We still want to get a 0 on the right-hand side. It's going to take us 2 steps to do that because we got 2 terms there. Okay. So you can choose to eliminate the 9 first, or you can choose to eliminate the x squared first. Up to you. Okay, so what most people chose to do, you got 7 plus 2x, and you got x squared minus 9. Most people chose to operate on the 9 first. So we have to add 9 to both sides. And there's what we get. Okay, of course, minus 9 plus 9 is 0. So now we can write now I'll notice that we could add the 7 and the 9. Okay, they're like terms, but we'll save that up until we get to the last step. And then that equals just x squared. Now I'll put the plus 0 here. And I'm not going to write the plus 0 in the next step because x squared plus 0 is just x squared. So I'm going to write 7 plus 2x plus 9 equals x squared. Doesn't hurt if you have the 0 there, but it kind of gets in the way and it doesn't make any difference. Okay, because x squared plus 0 is just x squared. And then what everybody seems to have done is they seem to have subtracted x squared from this side. And I think at least one person then added x squared on this side, but no, we're subtracting x squared from both sides. So we get this. And of course now x squared minus x squared is 0. And we have 7 plus 2x plus 9 minus x squared equals 0. Now, can we identify A, B, and C easily from this? Well, the answer is no. It's even a little bit harder because we've got 4 terms on this side. Well, let's put it in order with the squared terms first. There's just one of them, so it's x squared And then the x term next. And then just a plain number. But of course, we got two of them. We got 7 and we've got 9. Well, what are we going to do with this? We still can't identify C because C would be the 7 and the 9. Well, they're added. So we put this in the form minus x squared plus 2x plus 16 equals 0. And there it is. Okay, I don't think we have a lot of room left on this board. So if you're still taking notes, you got it? Okay. Okay, so let's try this. Okay. So what are we going to do here? Well, let's get rid of the x squared over here. In other words, let's get a 0 instead of an x squared. And the way we do that first, we write out what we have. And it really isn't a bad idea to have maybe a pencil and a pen or something of two different colors. So you can distinguish exactly what you're doing to both sides. But of course, if the last thing you have is what you're doing to both sides, you're going to be able to see it anyway. So don't require that, but there it is. Okay. Okay. And then minus x plus x squared is 0. Minus x squared plus x squared is 0. And here we have 5x. We could write plus 0, but 5x plus 0 is just 5x. So we can understand that the negative x squared plus x squared gives us 0 and doesn't contribute anything over here. Okay. That x squared is pretty bad, but if I smudge it, it's going to be bad too. Well, let's try it. Okay. Now what do we do? Well, first thing we do, you can do this, you write in ink. And make that just a little neater. Give myself room before the equal sign and do something in both sides. Okay, so this is plus x squared. And give myself some room here. And this equals then 5x. Really, I should have those equal signs lined up, but I didn't anticipate very well. Okay, so now what do we do? Well, we got 5x over here, 1 0 over here, and it's real easy now to get 0. We subtract 5x from both sides, and we get okay, so now we got 0 over here. Then we write all this in the order from highest powers to lowest powers. We've got an x squared here and an x squared here. So we're going to write 3x squared plus x squared. We got a 9x and a minus 5x. Now, depending on how secure you are with this and how well you're doing with the problem and whether you're getting the right answers or not, you could have maybe said, okay, 3x squared plus x squared is 4x squared. And you might not have to write out this step. But I recommend strongly anybody in this course writes out this step. Okay, until you really get used to it, until you've done 100 problems like this. Okay, 3x squared plus x squared is 4x squared. 9x minus 5x is 4x. Now, the only incorrect answer I got from one person said that we have 2x squared here. Okay, I might have been looking at this form and just made a little error. If you wrote it out like this, I think you would come up with a 4x squared. Okay, and remember where that came from. We had to add x squared to both sides here. And if you got a 3x squared and add an x squared, you do get a 4x squared. Okay, but that was done very well. And all the steps were written out nicely. And when I looked at it, I didn't see anything wrong with it. So I think it was just one little mental glitch that went on there. Okay. So what we're saying is all this can be done just by adding and subtracting things on both sides. And now we can identify A, B, and C. And you know, when I ask people to identify A, B, and C, yeah, everybody said 4 for B and 2 for C. One person said 4 for A. I mean 2 for A instead of 4. So I think that was done very well. And I hope we see where the 4 came from. I believe we do. Okay, we're going to spend the rest of the day just kind of pushing this principle of doing the same operation on both sides. Now, you can add or subtract same thing on both sides. You can multiply or divide both sides by the same non-zero quantity. Okay, those are the 4 things that you can do with equations. As far as this course is concerned, that's it. Okay. When you get into pre-calculus, then you get exponential and logarithmic equations and square roots and stuff like that. And there are other things that you have to be able to do. But we want to nail at least these operations. Okay, so no talking. This isn't a quadratic equation, okay? So you're not going to want to get equal 0 over here. The reason you want to get 0 on a quadratic equation is it has to be this way before you can use a quadratic formula, before we can identify A, B, and C. For a linear equation, what do we want to do? We want to get all the x's on one side and all the numbers on the other. Using valid operations on both sides. Okay, now, what most people are doing is they're getting a 0 on this side. It's not really what we want to do with the linear equation, but it's good practice for the operation. So let's see how that works and then see what we'd want to do instead. So we got 5x plus 3 equals 7x minus 5. What we do, if we want to get 0 on this side, it makes perfect sense. We add 5 here and we add 5 here. Well, this gives us 5x plus 3 plus 5. Now I could add the 3 and the 5, but I'm just going to leave them there because I want to really focus on what we're doing here. And that equals 7x. And then it's plus 0 because minus 5 plus 5 is 0. And then we could subtract 7x from both sides. We have 5x plus 3 plus 5 equals 7x. And we carefully write out minus 7x and minus 7x. Now, at least one person at this stage, and copying this, I'll put an X on that 5. There's no X on that 5. So you got to be careful that you write out exactly here what you have here. And in the next step, write it out carefully. And it might help that sometimes people bunch their expressions up. Make sure you have plenty of room between the terms that you write so you can clearly see what you've written. Okay, in any case, we can come down here and we get 5x plus 3 plus 5 minus 7x equals 0. Now, when I introduced this problem, I said, well, what we want to do with a linear equation is we want the x's over here and the numbers over here. So now we got x's and numbers on this side. So it's not really what we wanted to do, but it's not invalid. Okay. It's mathematically, this step is equivalent to this, in that any x that solves this will solve this. So we haven't done anything mathematically invalid. Okay, then we can write 5x minus 7x plus 3 plus 5 equals 0 in descending powers of x. And we get negative 2x plus 8 equals 0. Okay, because the 5x and the minus 7x, they're like terms, both x terms, you can add them. You can add the 3 and the 5. Now, we still don't have a solution. But from here, it's pretty easy to get a solution. We can say, okay, we do minus 2x plus 8 equals 0. And we subtract 8 from both sides. And that gives us minus 2x equals minus 8. So even though we took some extra steps because we tried to get a 0 here, still going to be okay. Last step. We divide both sides by negative 2. Negative 2 divided by negative 2 here gives us just 1. So that's just x. And negative 8 divided by negative 2 is 4. Then, if x equals 4, and for interest of time, there's one more thing I want to do before we're done. But so I'm going to just point to this. If x equals 4, then 5x equals 20. 20 plus 3 is 23. 7x equals 28, and 28 minus 5 is 23. So if we replace x by 4 here and here, we get, do the arithmetic, we get 23 equals 23, and that confirms that x equals 4 is your solution. Okay. Now quickly, I'm going to solve this equation again. This time, let's remember that the goal is to get this, okay? We want to get something like this, because then we can simply divide both sides by the coefficient of x. And we get our solution. And we get there a lot quicker if we do this, okay? 5x plus 3 equals 7x minus 5. I'm going to want just the numbers on this side. So I want to get rid of the x term on this side. To get rid of the x term on this side, I do 5x plus 3. First I write it out, equals 7x minus 5. Then we do minus 7x over here, because 7x minus 7x is going to give us 0. And we get 5x plus 3 minus 7x equals 5. Now, on the left-hand side, we want just x terms. So we're going to subtract the 3. 3 isn't where we want it. 3 is in the way over here. Got ahead of myself there. Okay, so we subtract 3 on both sides. and we get 5x minus 7x equals -8. Well, then 5x minus 7x is -2x. And then -2x over -2 is -8 over -2. So x equals 4. And we didn't go to the trouble of getting 0 on this side. We wanted just the numbers on this side. And that's how we solve a linear equation. Okay, well, we're out of time, but I think we're doing pretty well with this. Okay. Now this is board I showed you last time. I'm going to kind of go over it, point out a few things. If you know everything on this board, it's a good start. Okay, but of course you got to know how to use it. So, but first I'm going to just tell you what's here. Okay, collisions. And I'm reading this, I haven't read it before because I want to do it fresh, okay? Actually had a good night's sleep, took just a little bit of caffeine this morning, so hopefully I'll stay coherent throughout the class. Okay, collisions. Isolated systems of two objects, your forces are equal and opposite. It says F12 equals negative F21. That's notation you should understand because you read it in your book. It just means a force of particle 1 and particle 2 equals the force of particle 2 and particle 1, but opposite. Okay, equal and opposite force. That's Newton's third law. It's fundamental. That's why there's impulse momentum or angular impulse momentum. So you need to know that connection. Otherwise, you don't understand impulse momentum well enough to use it in an unfamiliar situation. And I guarantee you, your final is going to have some unfamiliar situations or familiar situations you haven't really thought through yet and need to think through. You're going to have those things. Okay, so that's Newton's third law. Okay, didn't even read long enough to see that I'd already written that, but I'm glad I did. I should have. There's some stuff I should have written here that I didn't. I'm working in. Okay, now this works for particles. What's a particle? Particle is something that doesn't have any rotation. And it can be modeled as a single point. For the purpose of gravitation outside the Earth's surface, the Earth is a particle. It can be modeled as 6 times 10 to the 24 kilograms, 5.997, I think. But 6 point, yeah, I haven't juggled it recently, so I don't remember if it's 6 or 5.997 or something like that. Real close to 6 times 10 to the 24th kilograms, concentrated at a point. Okay, now concentrated into something the size of a marble, it'd be a black hole. Okay, so I guess there's a singularity there, and it would act just the same on anything outside the surface of the Earth. You go beneath the surface of the Earth, go toward the center, gravitation actually increases for a while and then decreases. And we'll see in multivariable calculus why that is. Just Gauss's law, it's no big deal. Once you understand it. Okay. So for particles, it works. And it's true for extended objects too. Okay. 2 irregular asteroids collide in intergalactic space. Okay. They exert equal and opposite forces on them. Okay. Take 2 dominoes, which I did in lab last time, and bring them together, collide them, see how far they travel, see that they spin sometimes. Just looking at and just doing that to get some estimate of how far they slide, how far would this domino slide before the collision. I mean, if the other domino wasn't there, then what's a combination of how far the 2 slide afterwards? Okay, gives you an idea of how much momentum is conserved. And you can conclude how much energy is conserved too, whether it's an elastic or an inelastic collision. Okay, those are just examples of extended objects interacting. Okay, if I have that beam rotating and drop a magnet onto it, well, I'm going to probably screw up something. The whole thing will collapse and injure people. But if it works right, then you have the angular impulse on one is equal to the angle and opposite to the angular impulse on the other. In other words, the angular impulse on the magnet due to the rotating beam is equal and opposite to the angular impulse that the dropping magnet puts onto the beam. You know? Okay, it's because the forces are equal and opposite, and they happen at the same point, at the same length of time. Okay, and you conclude very easily that the torques are equal and opposite, which leads you to conservation of angular momentum, which is totally different than conservation of momentum. It's very much analogous. It's got different units. It's a different thing. And it's conservation of angular momentum that dictates that your planets orbit in ellipses, for example. And we've talked about that. You know, that the planet isn't going to exert a torque on anything out there any more than you can exert a torque on something out there by wiggling a rope back and forth like this and hoping the rope will move that object. Rope is flexible, it's not going to happen. Now, it's not a good analogy of gravity, but there it is. Okay, so anyhow, we have F12 equals negative F21, tau12 equals negative tau21 for extended objects. Extended objects is anything that can't be modeled as a point, it can rotate. Okay. And then we've actually derived 4 constant forces. And they're never constant, you know. Well, in some interactions, I guess they can be, but you know, they're typically not constant. The forces of interaction when something collides with something tend to have a graph that looks like this, kind of like a bell-shaped curve, but not really. But not too far either, okay? So you just kind of think of a bell-shaped curve, but don't think it's perfectly Gaussian, which means exponential of a negative square. Okay, so you got F12 delta T equals negative F21 delta T. You can express this on any little time increment where the force doesn't vary much, and do this as a sum of little time increments and take the limit as the time increment goes to 0 and get an integral that says the same thing. The integral of F12 dt is equal to the negative integral of F21 dt. Just very straightforward. You can go to the local, which is a small increment, and then the forces are pretty much constant. Searching for words, constant, that's a tough word. Okay, so we got same thing for torques. If the forces are equal and opposite and happen at the same point, then the torques have to be equal and opposite. So when you integrate them or just multiply by delta T, those products are equal and opposite. It follows that the total momentum of 2 objects would be the sum of the F delta T's. Okay. Change in the total momentum is a change in all the F delta T's. Okay. F delta T's in this, F delta T's in that. Well, the forces are all equal and opposite, so that sum is 0. And torques are all equal and opposite, so that sum is 0. Now, if you multiply, well, let's back up. I should have said it originally, but you multiply force times a delta T, and you get units of momentum. And if you derive this, the impulse momentum theorem, using the simple equation VF equals V naught plus AT with A equal to F net over M, okay, you get impulse here and momentum here. So this is a measure of impulse. It's also a measure of change in momentum, okay? And impulse equals change in momentum. Right here is the conclusion. And the analogous conclusion with angular momentum, I use delta L, and there's a subscript on this that's been smudged. It's been up here for at least a few years. It's holding up pretty well, but I have to redo it someday. But I kind of like it. Okay. Total change in momentum is the sum of all your torques times delta T. And a torque times delta T is a change in I omega. And it's, if you just know that I is the sum of all your MR squares, this becomes obvious. And omega, of course, is your angular velocity. So that sum has to be 0. So you have conservation momentum and angular momentum for isolated systems. I've only done it here for 2 particles, but if you got 3 particles, you can say all the same things. They're just 3 particles in your sum. Okay, and each particle interacts with each of the others. So there are equal and opposite forces between every pair. Now you can go on a little further with that, but there it is. Okay, gravitation, right there's your rule. Be sure you know it, be sure you can use it. It's not just negative G big M little m over R squared. It's multiplied by the unit vector R over R. And then, you know, probing what people understood over the last week, I find that people start still very conversant with vectors. Okay. Even though it has linear algebra and a lot of other stuff, the idea of a unit vector and so forth, it's a little shaky. Okay. Go back to chapter 1, make sure you're not shaking that anymore. I can't teach that to you now. Okay. We did it all early, and it's all in videos, they're all there for you. And you can also, you know, you have 78 million videos on this thing out there on YouTube and other sources. And of course, you have the materials for your course. Okay. Make sure you understand vectors as well as you possibly can. Also, if you're going to be taking multivariable calculus, it can be a real help to you because we start out assuming you know all this stuff. We go over it in about 15 minutes and then take off from there. Okay. Because by the time we get to the integral theorems at the last part of that course, we want to have time to do it because they're the central essence of the course. Okay. There are other central essences, but it's the one thing that ties things together in a way that's really going to be beneficial, especially if you're a mechanical or electrical engineer. Okay. Everything is written in terms of multivariable calculus. Okay. Vector calculus. So this is real important. So end of lecture, what you ought to do. Let's just see what's going on here. Okay. So you got a picture of this. You got a big mass, big M and little m. You got the force that big M exerts on little m. Okay. And your R vector goes from big M to little m. That's this vector. You divide by R without the arrow, which is a magnitude of R, you get a unit vector, and you multiply that unit vector by negative big G big M little m over R squared. So you have a vector here, your unit vector is in this direction, vector of length 1. You multiply it by the magnitude of the force in the negative, it's back this way because it's negative, and there's your force. It's in vector form, now you can operate on it. As long as you know how to operate on vectors, it's not that hard. Now, when you learn what you can do with all the vector operations, as we do in calculus 3 or multivariable calculus, then things get pretty complicated. Things get pretty conceptually difficult. Okay. The guy I talked about earlier, you know, probably the very likely the best physics student I've had in the last decade. I've had some really good ones, so can't even say that. And having a great career as an engineer. When he got to where he had to put all this stuff together at the end of physics and the heavy electricity and magnetism stuff, he said, man, this stuff is hard to understand. Yeah, really smart guy. Maybe it was just the way I was saying it, but he's getting it out of a good textbook also. He still found it hard to understand. Okay. Okay, well, there it is. You got to know that. And then, of course, here's the force of this object and this. So if this is the Earth and this is you orbiting out there somewhere, hopefully with some kind of protection, so you stay alive. You know, Earth is pulling you. You're also pulling the Earth. You got to know that. Okay. And if it's good heavens, I forgot the name. Get Didymus and maybe Didymorphus, I don't know. You know what I'm talking about? Been paying attention to the world? Probably not, because you're in an engineering curriculum. And one of the great engineering feats was that launch a year ago. You know, still, you know, out there, I think, by this date. a year ago. It's pretty close to coming back. Actually, I'm confusing that with the moonshot, but they both happened last year. Here's one where they collided with the asteroid. You know what I'm talking about? Got this chunk of metal spacecraft up to about 30,000 miles an hour and crashed it into a moon of an asteroid to see what happened. Okay, and it turned out it was pretty spectacular. If you just go with impulse momentum for that collision, which is going to be using angular momentum and everything, okay, that collision was supposed to change the orbital period of this asteroid around the bigger asteroid by maybe 3 minutes or something like that, change it by a lot more. Well, I immediately thought, well, the only way that happens is because this thing hit and ejected a lot of material. So there's a change in momentum when it hits. And then you take the kinetic energy of this thing and blow out a lot of material, and there's a big change in momentum there, which is exactly what happened. I would have been able to quantify it. I don't have the material science data. And I could quantify it up to an extent, but rocket scientists and NASA all know more than I do. So they were able to refine it much more than I could have. Okay. So everything I could read about that was really interesting. Well, that's just an example of everything I've talked about here. We got the gravitational attractions and the gravitational attraction of the bigger asteroid of the little one. And then what happens to the orbital period when you change the momentum of this one. And that comes back to universal gravitation. So you got this and this. Very interesting. Okay, well, I know you want me to spend the rest of the hour talking about that, but I'm not going to. Okay, so we're going to move on. I actually put this in the form of multivariable calculus. It even says in multivariate ignore. Okay. I said that the force is the gradient of the potential energy. Okay. Now, gradient is actually something that's real easy to calculate. I could teach you to do it in 10 minutes. Okay. But we're not going to do it because we're going to do it in multivariable. It's not bad. But then the meaning and how all that comes together and becomes one of the most important topics in mathematics as applied to at least mechanical and electrical engineering, if not a lot of others. Okay. Also civil stresses and so forth. Anyhow, and others that I'm not thinking of because either I don't know or because there aren't any. I say it's because I don't know and because I can't think of. Okay, so your force is equal to the rate of change of your potential energy. Okay, your net force or your conservative force. Okay, I probably should have put a conservative on this. But we're applying this to gravitation. Because of this, your potential energy is negative big G big M little m over R, meaning that you would integrate this to get this. This is like a derivative. So if this is a derivative of this is an integral of this. Well, we've already integrated to get the potential energy due to gravitation. This is potential energy relative to infinity, P equals 0 and R equals infinity. I'm glad I said that. As I go through this, I'm not looking at what's coming next. I'm saying what ought to come next, and so far it is, but we'll see that, hey, I'm sure I didn't get that 100%. Okay, so there it is. Right here is a picture of potential energy versus distance. Okay. Potential energy approaches 0, right? It's always negative if it's 0 at infinity, because the work it takes to go from 0 to infinity against a gravitational field is positive. Change of potential energy is equal and opposite to the work done by the conservative force, so it's negative. You got, yeah, that whole definition, change of potential energy is equal and opposite to the work done by conservative forces. That's a key. If that isn't right there in the center of your mind now and for the rest of your career, you're missing something. And you're missing an important thing that you need to know for your engineering. They're probably going to really need to know that something. Okay? Because in engineering, they're bigger about teaching you to get the right answer than the principles. I mean, they teach principles too. Now, I've been through an engineering career, but went to an engineering school, basically, a lot of top-notch engineers, okay? So I think I picked up something by osmosis. And I've become interested in the thing over the last 150 years. Okay, there it is. This is important. These definitions are important. Make sure you incorporate and internalize as many as you can and know when you're applying the definitions, not just when this formula gives you the right answer. Now, if you're practicing an engineer, by all means, make sure you use the right formula to get the right answer, but then check it out at a deeper level, which involves the physics. And typically involves other things too. Okay. Again, I quote this. This is just the force as a derivative of potential energy with respect to position. Okay. If that's the case, then the force is conservative. Any force that's a derivative of a potential energy is a conservative force. Any conservative force is a derivative of its potential energy. That's all there is to it. And then I say the word from A to B is potential energy at B minus potential energy at A. Okay. Now, let's see if I said that right, because I always get that backwards. You know, everybody's really stupid about something. I mean, I'm stupid about a lot of things, but that's one of them. Okay. I think I maybe have that backwards. Let's test that against my cinder block. I should have a cinder block here, but then I probably hurt myself. Okay, if I lift a cinder block, okay, my potential energy here is less than my potential energy here, right? Now, did I do positive or negative work? I did positive work. If I subtract the potential energy here from the potential energy here, I'm going to get positive, right? Because it's higher here than it is here, because of the fact that the potential energy is equal and opposite to the work done by the conservative force, and you've got to work that out until you really understand it. So this is actually right. Let me make sure. So it's negative big G, big M, little m over R2 minus big G, big M, little m over R1. And is that right? Okay. If I'm moving away from the planet, the work done by the conservative force is positive. Meaning if R2 is bigger than R1, the magnitude of this thing is less than the magnitude of this, because you divide by a bigger number, you get a lesser number. And the minus and negative gives you positive here. So the bigger one is positive and the one of less magnitude is negative. Okay. So yeah, I got that right. I've always got to check that out. And you know, I say that, I mean, I could just assert this and say, there it is. But there's a simple connection that allows you to always check out your results with a little bit of intuition, if you develop the intuition to reason that out. Okay. And I really urge that you do. Okay. In a circular orbit, gravitational acceleration equals centrifugal acceleration. So we get this equation that I'm not even going to read to you because you didn't have any trouble with it when I said this. If you know this and you know the gravitational acceleration is what you get when you divide this by little m, and know centrifugal acceleration is v squared over r, you don't need to know anything else. You can solve that equation in 4 seconds flat and get velocity as a function of little r and big M. Then I mentioned that the escape velocity is a very similar formula, but it's twice as much as the velocity that you would have in an orbit at that distance. Okay. And that just comes back to the energy. You just integrate the energy from here to infinity. Okay. and then figure out what V has to be to have that much, it's 1/2 mv squared equal to that interval. And this is what you get. Very simple. Okay. And you should know that. Okay. If you don't know the physics at that level, you don't really know the physics. Now, in a first semester physics course with any rigor, very few people really know the physics in all its aspects when they get to the final, and they have to fake it sometimes. The less you have to fake it, the better you're going to do. Okay. Of course, if you're really good at faking it, okay, maybe you're going to ace it. And I knew people, okay, I knew people who faked it mostly through math, because I ended up in math. I started in physics, and there were people who just, made much better grades than I did, made a lot more A's than I did as undergraduates by faking it, and then they got to graduate school, couldn't do anything. Okay, whereas I, by just nature, not by any virtue or anything, just really couldn't bring myself to fake it, so I didn't make as many A's as these people did. But in graduate school, I could do stuff that they couldn't, because they got to the point where you can't fake it anymore. Well, engineering's analogous. Okay, talked about level of incompetence earlier. Okay, everybody rises to their level of incompetence, and as I said, the higher your level of incompetence, the more interesting and lucrative your job is probably going to be. So become incompetent at the highest level you can by becoming competent at the most basic level. Okay, well, there it is. And again, if your engineering instructor is a friend of mine, says differently, believe him. Okay, he knows engineering a lot better than I do, but I think we've had a lot of conversations. Either he's being polite or says, this guy's too ignorant to argue with. I'm just going to agree. He says that to me, not me to him. He knows his field, so listen to him before you listen to me. But I think we're agreeing. Okay. Anyhow, from this, kinetic energy is 1/2 mv squared. If you put this in for V, right there's your kinetic energy. So your total energy is potential plus kinetic. Your potential energy, which I never actually do. Yeah, I did here. Okay. I derived it right here and I didn't remember doing it. There it is. Okay. And I just went over it. Here's your potential energy. Here's your kinetic energy atom, and you get this. So if you want to change from this orbit to that orbit, this is the quantity that changes. This is how much fuel you need. Or this is how much kinetic energy you're going to need if you come down from that orbit. Okay, and that can be dicey because, of course, you come down from an orbit so that you can re-enter the Earth. You don't want to be going too fast. So you got to have enough fuel to slow yourself down, which is equivalent to the amount you would need to feed yourself up. Yes, feed yourself up. Okay. I got a little note in purple here that applied to this. Potential, I think it applies to this. Potential energy is this. We integrate this from R to infinity, and that's where this came from. That's where this came from. So that's kind of an addendum. Also, the analogy to this gradient thing is just F equals the X derivative of the potential energy if you're just talking about one direction. For example, totally relevant to the problems I emailed you, the magnet in the car. You got the potential energy curve, you take the derivative, you get the force curve. If you got the force curve, you integrate it to get the potential energy curve. That's something you should have understood back when we did it originally, but it's all booming, buzzing confusion at that point. And if that's the case for you, pull it together now. You have 12 days. Okay, at the latest. Okay, so there we have it. Then a change of potential energy equal and opposite to the work of a net conservative force. Total all conservative forces, which I've said, there it is in writing, so that you have no excuse for not understanding that it should be there. Now, you have an excuse if you don't get all this completely sorted out and make 100 in the exam because you have finite time. And not many people actually have the ability to pull it together that way, okay? Even if you have time. But everybody has the ability to pull it together well enough to do okay. I can verify that. I've seen what you all do. So we can at least we can do it very well. Okay, and everybody can do that. And everybody give them more time, I think, to do it quite well. Okay. So we've gotten into a time crunch. Well, everybody's in a time crunch all the time. Okay, including me. Okay, elliptical orbit, the planet at the focus. Here's what I talked about before. The fact that your planet cannot exert a torque because the force it exerts on anything orbiting it is toward the center. Moment arm is zero. Okay, or the lever arm. Okay. Torque is zero. And I say torque is zero. And I could have said this a little better if I'd have put a net on this. You can't read the word net, but you probably know what I'm writing here, N-E-T. Most of you can spell net. Okay. Net force. Net force is radial, moment arm is zero. Okay, no torque. This implies that the angular momentum doesn't change. Now, you can connect that to the fact that it's elliptical orbit. You probably want to go to the polar equation of the ellipse, which people aren't very familiar with. And I've kind of given up on doing that one. Okay. Until we get over the COVID depression in education and people actually get totally rigorous for calculus 2 course. Okay. I can expect everybody does. I mean, if you had it here from Will, you've had a really good one. Not, and if you've had some courses from me, you've had a good course, but it's not where we'd like to have them right now because of various factors. Close. You can get there from where we are. Okay. And doesn't seem to handicap people much when they get into the engineering curriculum. So second half of the engineering curriculum with tech, I think we get everybody prepared pretty well. Okay. I know some of my grandson's buddies were terribly badly prepared. Okay. And they succeed in a very rigorous program. So you're smart, and you are, you can do it. Still, learn as much of this as you can. Okay, anyhow, angular momentum doesn't change. Angular momentum doesn't change. Well, angular momentum is the product of how far you are with the component of your velocity perpendicular to how far. It's your omega. Okay. If you're closer, your omega has to be a lot bigger to have the same product with your distance. That's all there is to it. So that's why I say your orbit has to be faster when closer because you have to have the same angular momentum in here as you do out here. Okay, out here, you multiply this distance by this velocity. And in here, you multiply this distance by this velocity. This distance being smaller, this velocity's got to be bigger. Another way of seeing it, of course, is conservation of energy. You're out here, you've got much more potential energy than you have in here. The potential energy is negative, but it's more negative here. You lose potential energy going from here to here. Where does it go? There's no dissipative force out there, or at least it's negligible. Okay. It's got to go to kinetics. The kinetic energy has to be bigger here than it is here. For both of those reasons, and both reasons you should understand, because they're very fundamental. You're going faster here than you are here. You expect that decent probability you're going to encounter a problem that requires you to understand that. Because you probably don't have a formula for it. You're probably not going to remember a formula for it. You got to reason it out from energy and or angular momentum. I may even ask you to explain it one way or the other, then explain it the way you didn't. Okay. Okay, now this is actually equivalent to one of Kepler's laws. Okay, it says that you sweep out equal areas. You know, this radial vector sweeps out equal areas in equal time. Okay. That means Out here, it doesn't have to be going too fast to sweep out a certain area. To sweep out the same area in here, it's got to move like crazy. It's just a consequence of conservation of angular momentum. And Kepler didn't know that. Didn't have to work that out and explain why. Kepler had to leave something for Newton to do. Newton's kind of the pinnacle up to Einstein. And nobody's discovered me by now, so I guess it'll stay that way. I think people have discovered exactly what they've got here, so I'm not in the running. One of Kepler's laws, okay. Sweeps out equal area to constant rate. Sweeps out area to constant rate with respect to time. Equal areas and equal time. Simple harmonic motion, which is the latest thing you've had to deal with, okay? But you've been dealing with it ever since we did energy, because you've had things about springs and stuff like that. So you should have nailed the energy aspects of simple harmonic motion. Doesn't mean you did, should have. Okay, and if you didn't, do it. Okay. So let's see, am I blocking the board? I'm blocking some of this, but I'm okay here. We're going to move this over. Okay. First of all, your kinetic energy is 1/2 mv squared. Okay. Now, I say that's equal to 1/2 m times omega a sine of the quantity omega t squared. Why did I say that? Because that's what your velocity is. I don't have a phi on this, but if your position is a cosine of omega t plus phi, and phi is 0, so it's just a cosine of omega t, what's the derivative? Negative omega a sine of omega t, right? And that's your velocity, derivative of your position. Or the horizontal projection of that vector I showed you on the unit circle, or the actual circle of radius a, a week ago. Last Wednesday, 5 days. Okay, so V is this. And if you work this out, well, you got another expression for kinetic energy. Now what I say here is theta is a cosine of omega t. Okay, assuming phi is 0, and if phi is there, here it's going to be here. So it's not going to make any difference in the expression. If x equals a cosine of omega t, then you get this. Okay. And also you get a 1/2 I omega squared if you're doing angular simple harmonic motion. Okay, now we're probably going to flesh some of this out a little bit because it's new. But your potential energy is the integral of your net force with respect equal to opposite to your integral of your net force, opposite to the integral of your net force. Your premise, which I implicitly assume since this is new, you know, is that your net force is negative kx. And I didn't write that down. And I'm going to write a couple of things down here, especially if I find a pinkish red chalk. It's F net equals negative kx. You can see that. And x isn't very good, so let's see if we can fix them. They are. And that equals negative k theta. Either way, you get the same form. You get theta equals a cosine of omega t plus phi if you need to include the phase angle. That's important for a lot of problems. That applies equally well to x or to theta. This is for angular motion. This is for linear motion. Okay. The units are different. The units of A are going to be what? They got to be same as units of theta, they're radians. Here your units of A are the same as units of X, SI units would be meters. Okay, so A could be in radians or meters, depending on whether you're talking about that beam oscillating back and forth. And one of the problems in there, incidentally, I still haven't worked it out. There's something in there that made me hesitate a little bit. I was trying to get to the heart of why that thing oscillates. Okay, so one of the problems delves into that. And most of the problems, incidentally, don't give you numbers. They just ask you questions about the system. Because I want you to focus on the questions rather than the formulas. Okay, I think, you're not going to master them all. Don't spend every available minute between now and next week when you take the final, whenever you happen to take it during the week, trying to figure out those questions, but do spend a significant amount of time, I'd say maybe half your preparation time with those questions. Now it's up to you. How do you balance it? You want to spend your time memorizing formulas you're never going to remember after the final, learning tricks to get by. You balance it. Bottom line is scoring the final. Okay, whatever gets you there is okay, but I think these problems will help you get there. So I recommend you spend some time thinking about them and start as soon as you can, so that they percolate in your mind for a week or more. It'll cause you to see things differently. It might cause you to beat your head against the wall, which will cause you to see a lot of things different. So don't do that unless you got a fairly spongy wall. Okay. Well, okay, there we have it. From the differential equation that everybody can solve, at least one person did on the last exam when we hadn't even covered it. Okay. You get this, and I did that last time, so you can review it there. Potential energy is equal and opposite to the net force, which is negative kx. And you know what? I never saw this before. I've got generations of physicists out there who are thinking there's a 1/2 in this interval. There isn't. Yeah, 1/2 doesn't come out till you integrate that blame thing. If you integrated that, you'd end up with a 1/4. So I don't know how many times I've looked at that and not noticed that, but there it is. Okay, so that's a long-standing error. If you took a picture of that, fix it. I'll post another picture of this, just so probably obliterate the other one. So if you got that one bookmarked, go back to the assignments page and bookmark this one. If you got a photograph on your phone, you might want to take another one. Okay, there you have it. And that is your potential energy. The force is negative kx. You integrate that, you get negative 1/2 kx squared. The potential energy is the integral of that force, which is this, and also integral from equilibrium to x. But now I've got the same variable as my, what should be dummy variable in here. Well, you can deal with that. I should officially have a different variable here, like this. That's a good variable to use for x. Okay. Won't do that there. Okay. Now, since non-conservative force is 0, remember that the conservation of energy, and I'm not talking about that. That was before the midterm. Okay. People did reasonably well on the midterm in most cases. I'm not reviewing that. I'm reviewing what we've done since midterm. So remember that your conservation of energy comes from the kinetic energy theorem, okay? Which is, if you integrate, find the work done by the net force, turns out that's equal to the change in kinetic energy. Derive it from constant force by plugging A equals F over M into the V squared equals V naught squared plus 2A delta S equation for uniformly accelerated motion, which you should be able to derive. Okay. Okay. You do that. And the work done by the net force is equal to the change in kinetic energy. All there is to it. Now, the net force could contain conservative and non-conservative. So it's the work done by the conservative forces plus the work done by the non-conservative forces. Okay. If there are no non-conservative forces, you end up with kinetic energy plus potential energy is constant. If there are non-conservative forces, this and this add up to the work done by the non-conservative force. Actually, I think negative of that word, but yeah, there it is. Work that out. Okay. I think I said something wrong there, but I'm not going to correct it. Just make sure you got that worked out. So that in the case of simple harmonic motion, kinetic energy plus potential energy is 1/2 mv squared plus 1/2 kx squared. Okay. Now we haven't done this, but you can throw that together with this formula. And with a x equals a cosine of omega t, or if you wish, theta equals a cosine of omega t, doesn't matter. How are you going to get this? It's going to be this with the sine of omega t squared. That's what you get for the kinetic energy, because this is your velocity. And for the potential energy, it's x, which is a cosine of omega t, that's squared. Well, you're going to have a sine squared and a cosine squared, right? From all this. And when you do all this and finish up the arithmetic, you actually have an a squared sine squared and an a squared cosine squared, which add up to 1, and you get omega. And this is what you get. It follows that if omega is the square root of k over m, your kinetic plus your potential energy is 1/2 k a squared. Put it all together. Okay. Now I'm going to kind of leave the details of that to you, but if you want to ask, I really need to work it out on the board. I can't just say it because there are complications here. If omega equals k over m, then omega squared is k squared over m squared. And you got a k here, and then the square root of that is the square root of k over. You got a k here, and you divide through by this mass, and everything works out. But it's too much to just do with handling it. Okay, so we've got all that. That's pretty much a picture of the tools you need to solve problems involving kinetic energy, involving simple harmonic motion. You have energy conservation, you have the equations of motion. Now the equations of motion are implicit. If this is a cosine of omega t plus phi, which it should be generally, the equations of motion are the equations for x, v, and acceleration a. If you got x, take the derivative, you get the v function. Take the derivative of that, you get the a function, right? So I haven't even mentioned those, but those functions are important for solving the problems. Okay. Now, I have some general advice. Hope Zoom isn't getting fatigued. I've never taught this long in one Zoom section. Because I usually like to do it interactively, give you something to do, see how you do, talk about it. That's not going to happen today. Just because we've got to shove all this stuff into 2 classes. Okay. Questions you should ask. Given a problem, I'm abbreviating some. Do we have particles or extended objects? Right? Because what you're going to do is different. If you have an extended object and try to use linear quantities, equations of linear motion, the mass, okay? The velocity as opposed to angular moment of inertia and angular velocity, okay? You're dead. Okay, that's exactly what Chat GPT 2.5 did when I asked it a question about those dominoes. Okay, say, well, you use conservation of energy, and I did 1/2 mv squared and all that stuff. Okay, he said, no, you can't do that. It's, oh yeah, you're right. And then it went on and did something else ridiculous. After about 12 questions, it was giving me pretty good stuff. Okay. Now I don't know where artificial intelligence is going to be in a year, but I think it's kind of growing exponentially. I think there may be a logistic nature to that curve, but what I do. So my son-in-law would be able to come in with my daughter and grandson. So we talk about some of this stuff because he just finished his PhD in computer science. Okay. I had to stay home with the dogs. So the dogs have cost me insights that I could be sharing with you. But they're good dogs, so don't be upset with them. And they're also in Texas, so you can't do anything to them. Okay, particles of extended, do we have particles or extended objects? I can't write simple words here. And you're going to do something different. Okay, if it's particles, you're going to look at M, V, P, one half mv squared, etc. If it's extended objects, extended, not external, you're going to look at moment of inertia, omega, L, one half I omega squared, etc. Here you got conservation momentum. Here you got conservation of angular momentum. I recommend that you ask yourself this question before you start a problem, do what ChatGPT did. Okay? You're way smarter than ChatGPT, but you don't have access to the loads of information it's been trained on. Okay? Now that's ChatGPT 2.5. 4.0, I think, would do much better. And in a year from now, I can't even predict how good it's going to be. Still, as ChatGPT 2.5 warns you, check this out yourself because there's no guarantee this is anything but a hallucination. Okay? They don't say it that way, but that's what you got there. You're gonna have to learn to work with these things. It's going to be a big part of your work in the future. I'll be interested to see what engineering education at the best schools does, or at all schools. I mean, there's no engineering professor who doesn't understand this is a big deal. Okay, how do you work with this thing? How do you make sure it's not hallucinating? How do you make sure it makes sense? You got to understand the principles. Or if it tells you, well, use this software package. Well, you got to know the software packages well enough to be able to make a judgment. Some things just need the software packages. Ultimately, the question I asked it the other day required, it was a different question, but it required software packages. And I was mainly probing it to see if that was really true. I couldn't prove or disprove something. Actually, I thought I could and I was right, but I wasn't sure. Okay, well, anyhow. Got to do those kinds of things. I don't know if how much sense that makes to you right now, but it's important. Okay, a given problem, particles or external object, it's going to be one of these two. Okay. Isolated system. Okay. If it's yes, I don't know what's the symbol used here, is that it? There's a way to do yes or no. I don't do flow diagrams. Probably should, but I'd never liked to. It's not that it's difficult, it's too structured. But it's a structure you can work within. Okay, well, anyhow, I'm just gonna say yes or no. Momentum, negative momentum are both conservative. It's an isolated system. Okay. No. This ain't so. Okay. And then you got to consider external forces. And you got to kind of step back and have this kind of perspective. Okay, this kind of guidance in how to think and approach some of these things. Does that make sense? Now, my original idea before I made up the problems that I've given you, that I've emailed to you, my original idea was to give you a big old flow diagram, just make it, okay? Yeah, that could be useful. I got sidetracked with the problems. It took me a long time to write the problems. Okay. Typically, I go to a situation with the lab and I start asking obvious problems. And what happens is I say, okay, well, what if we modify this? You know, what if you don't have two descending fixed masses? What if one of them is a chain? Oh, there's some harmonic motion. Okay. These things occur to me as I'm writing the simple problems. So I just throw them all in. And then I try to make sure I've stated it correctly and coherently. This is a beta version, don't expect miracles, but I think most of it's pretty good. Okay. I told my wife, don't interrupt me, I'm creating miracles every day. She interrupted me anyway. Yeah, that's probably a good thing. So I'm going to give you a lot of this stuff next time if you think that's what you need. Okay. And I think that's going to be better than doing just a lot of examples because I can't do that many examples. If you want examples of anything, in that problem set, I'm giving you numerical examples for 4 or 5 of them that I think you can at least start to work through. Sometimes there's a tough question buried in there, usually toward the end, but sometimes even in the middle. In which case I say in the next bullet, now, if you didn't get that, it's okay, you can still do this. Okay. I think I said that when it was necessary, at least a couple of times. So take that for what it's worth, but this is kind of where I'm inclined to go next time, but y'all tell me, okay? So get into the problems that I sent out, do some review, reread the book, well, at least reread the chapter reviews. If there's stuff you don't understand, set out priorities. Like, I don't understand this, but I think maybe I'm close. I'm gonna put that as a high priority. I don't understand this, and I know I'm never going to, so forget it. You know, or I don't think I'm going to be able to understand this, but I know it's really important, so I'm going to spend a couple of hours on it. Stuff like that. Does that make sense? Review your problems, review the situations. You ought to be able to, at this stage, just read the problems in the book like a novel. And say, yeah, I can do that, I can do that, I can do that. What the heck's that? No, okay, I can do that. I think I could do that. I'm at least familiar with that. It gets you familiar with the way you have to think rather than just asking questions about what numbers do I plug into what formula. You probably get by knowing a bunch of good formulas if you're pretty good at making decisions. It's probably going to bite you if you rely on it, depending on your memory, depending on your approach, depending on all kinds of things. So you decide for yourself. Basically, I'm just telling you, here's the landscape. navigate it as best you can. Let me know what I can do to help. Okay.